Hello and welcome to G Fun Facts Online. Imagine holding a rock that's older than the Earth itself. A rock that has traveled through the cold, silent void of space for millions, sometimes billions of years, carrying secrets from the very dawn of our solar system. These aren't just any rocks. They are meteorites, pristine time capsules that allow us to map the unseen history of our cosmic neighborhood. Today, we're becoming cosmic cartographers, using these celestial travelers to piece together the epic story of how our solar system came to be. To read the stories these rocks tell, we first need to learn their language, which starts with classification. Traditionally, we group them by what they're made of: stony, iron, and stony-iron. But for scientists, a more revealing division is between chondrites and achondrites. The vast majority of meteorites that fall to Earth are stony meteorites. This group is split into two crucial subgroups. First, you have the chondrites. These are the most primitive, the original building blocks of planets. Think of them as sedimentary rocks from space. Their defining feature is the presence of tiny spherical particles called chondrules, which are believed to have formed as molten droplets in the swirling gas and dust cloud, the solar nebula that birthed our sun and planets. Because they've remained largely unchanged for over 4.5 billion years, chondrites give us a direct snapshot of the ingredients of the early solar system. The other subgroup is the achondrites. As the name suggests, they lack chondrules. These are igneous rocks, meaning they were once molten. They come from larger parent bodies, like big asteroids, that got hot enough to differentiate. That is, to separate into a core, mantle, and crust, much like the Earth. Achondrites are fragments of these shattered protoplanets, giving us a look into the geology of these long-lost worlds. Then we have the iron meteorites. These are incredibly dense, composed almost entirely of iron-nickel alloys. They are the actual metallic cores of those differentiated planetesimals. Imagine a young, growing planetesimal heating up, with heavy iron and nickel sinking to its center. Then a catastrophic collision shatters it, sending pieces of its metallic heart flying through space. When you cut and etch these meteorites, they reveal a stunning crystalline pattern called a Widmanstätten pattern. This pattern can only form as the metal cools incredibly slowly, over millions of years, something that could only happen deep inside the insulated core of a large asteroid. Finally, there's the rarest and arguably most beautiful group, the stony-iron meteorites. They are a spectacular mix of metal and silicate minerals, believed to come from the boundary between the core and the mantle of an asteroid. One type, pallasites, features crystals of a green mineral called olivine embedded in a shiny iron-nickel matrix. They are breathtaking. The other type, mesositerites, are jumbles of broken rock and metal, likely formed when two asteroids collided violently, mixing molten metal from one with the solid rock of the other. So we have these different types of rocks, but how do we know how old they are? This is where radiometric dating, our cosmic clock, comes in. Scientists use the predictable decay of radioactive elements to wind back time. The gold standard for dating the oldest materials is the uranium-lead system. This method is used on tiny, light-colored specks found in chondrite meteorites called calcium-aluminum-rich inclusions, or CAIs. These are thought to be the very first solid materials to condense from the hot gas of the solar nebula. By measuring the ratio of uranium to its decay product, lead, within these CAIs, scientists have pinpointed the age of the solar system with incredible precision, about 4.567 billion years old. This date is time zero, the moment the first solid matter began to form. But what about later events? For that, we use other clocks, like the potassium-argon system. Radioactive potassium-40 decays into argon-40, which is a gas. This clock doesn't tell you when the rock first formed, but when it last cooled down enough to trap that argon gas. Different minerals trap argon at different temperatures. So a meteorite might have an ancient uranium-lead age of 4.5 billion years, but a younger potassium-argon age of, say, 1 billion years. This tells us that a billion years ago, something happened, like a major asteroid impact, that reheated the rock and reset its potassium-argon clock. It allows us to decode the thermal history of a meteorite. We can even figure out how long a meteorite spent traveling through space. This is done by measuring rare isotopes called cosmogenic nuclides. As a meteoroid zips through space, it's constantly bombarded by high-energy cosmic rays. These rays create these special nuclides. The longer the meteoroid is exposed, the more of these nuclides build up. This gives us its exposure age, telling us how long its journey to Earth took after it was chipped off its parent asteroid. It's like a cosmic tan line. With these tools, we can reconstruct the entire process of planet formation. It all starts in the protoplanetary disk, that spinning cloud of gas and dust around the young sun. First, the CAIs condense from the hot gas. Then, chondrites form, perhaps in shockwaves rippling through the disk. These tiny bits of dust, CAIs, and chondrites start sticking together, a process called accretion. They form bigger and bigger clumps, growing into bodies kilometers across, called planetesimals. Chondrite meteorites are our physical evidence of this stage. They are literally leftover, fossilized planetesimals. As these planetesimals grew, heat from the decay of radioactive elements, especially aluminum-26, built up inside them. If they got big enough, this heat was enough to melt their interiors. This is when differentiation happens. Heavy metal sinks to the center to form a core, and lighter rock floats to the top, forming a mantle and crust. Achondrite meteorites are the proof of this planetary maturation. They are broken pieces of these differentiated worlds. The asteroid 4 Vesta, which we can still see in the asteroid belt today, is thought to be a surviving protoplanet from this era, and a whole class of achondrites, the HED meteorites, are believed to have been blasted off its surface. So by looking at a primitive chondrite and then an evolved achondrite, we are seeing the key steps in the construction of a planet. The story gets even more profound when we consider the origin of life on Earth. How did a barren, hot early Earth get the ingredients it needed for life to begin? Meteorites may have been the cosmic delivery service. A special class of chondrites, called carbonaceous chondrites, are rich in carbon, water, and a whole host of organic molecules. The most famous is the Murchison meteorite, which fell in Australia in 1969. When scientists analyzed it, they found dozens of amino acids, the building blocks of proteins. And these weren't just any amino acids. Their structure confirmed they were extraterrestrial. This was huge. It meant the raw ingredients for life weren't unique to Earth. They were being formed out in space and delivered here. Since then, we've found even more in these meteorites, including nucleobases, which are components of DNA and RNA. What about water? The early Earth was likely too hot to hold onto much water. It's thought that a significant portion of our oceans was delivered later by water-rich asteroids and comets. And again, carbonaceous chondrites are the prime suspects. They can be up to 20% water by weight, locked away in their minerals. The chemical signature or isotopic composition of the hydrogen in their water closely matches the water in Earth's oceans, suggesting they were a major source. A recent study even suggests this delivery happened very early in Earth's history. One of the most cutting-edge areas of meteorite research is using subtle variations in elements to map the early solar system. It's called isotopic cartography. By analyzing isotopes of elements like chromium and titanium, scientists have discovered a fundamental split, a great divide in the material that formed our solar system. Meteorites fall into two distinct isotopic supergroups, the non-carbonaceous, or NC group, and the carbonaceous, or CC group. The NC group, which includes most of the meteorites from the inner solar system, formed in a region closer to the Sun. The CC group, which includes those life-bearing carbonaceous chondrites, formed farther out. This means there must have been a physical barrier preventing material from the inner and outer solar system from mixing for millions of years. The most likely culprit for this barrier: the giant planet Jupiter. As Jupiter grew, its immense gravity would have carved a gap in the protoplanetary disk, acting like a giant wall separating the two regions. The inner NC reservoir was hot and dry. The outer CC reservoir beyond Jupiter was cold and rich in water ice and organic molecules. This also relates to the snow line, the distance from the Sun where it was cold enough for water to freeze into ice. Asteroids forming beyond the snow line could become water-rich, like the parent bodies of the carbonaceous chondrites. These isotopic fingerprints are allowing us to draw a map of the chemical geography of our solar system when it was just a baby. While most meteorites come from the asteroid belt between Mars and Jupiter, a very small, very precious few are visitors from other worlds, our Moon and Mars. These rocks were blasted off the surface of their home worlds by massive asteroid impacts, traveled through space, and eventually landed on Earth. The first lunar meteorite was found in Antarctica in 1982. At first, scientists thought it might be from the Apollo landing sites, but its chemistry was slightly different. It came from a whole new region of the Moon. We now have hundreds of lunar meteorites, giving us a much more diverse sample of the Moon's surface than the Apollo missions could provide alone. Even rarer are meteorites from Mars. We know they're from Mars because when scientists analyzed them, they found tiny pockets of trapped gas inside. The composition of that gas perfectly matched the Martian atmosphere as measured by the Viking landers in the 1970s. It was a direct atmospheric sample from another planet. One of these Martian meteorites, Allen Hills 84001, became world famous in 1996 when scientists announced they had found what looked like microscopic fossils of ancient bacteria inside. The claim is still hotly debated today, but it sparked a revolution in the search for life on Mars and helped create the entire field of astrobiology. This entire field of discovery is driven by the human quest for knowledge and treasure. Modern meteorite hunters are a dedicated mix of scientists and amateur enthusiasts who scour the globe for these fallen stars. They might chase fireballs reported by eyewitnesses, hoping to find a fresh fall, or they might systematically search deserts like the Sahara or the ice fields of Antarctica. In these desolate landscapes, a dark rock stands out, making it easier to spot a potential cosmic visitor. The hunt can be very lucrative. A beautiful palisite meteorite found in China called the Fukang meteorite is estimated to be worth over 1.5 million pounds. But for most, the thrill is in the discovery itself, the chance to be the first person to hold a 4.5 billion-year-old rock from the heart of a long-dead world. Once found, a piece of the potential meteorite is sent to a lab for official classification. If it's confirmed, it's entered into a global database and given a name, usually after the nearest town or landmark. This ensures every discovery is documented and made available for scientists around the world to study. So from the first grains of dust in the solar nebula, to the building blocks of planets, to the delivery of water and the seeds of life to our own world, the entire history of our solar system is written in these stones. Meteorites are a finite, precious library with its pages scattered across our planet. And as we continue to find them and develop new ways to read their secrets, we will continue to map the unseen landscapes of our cosmic past, bringing the epic story of the heavens down to Earth. Thanks for listening to G Fun Facts Online.